Imagine living in a time when math books were forbidden to you. Imagine being forced to study in secret by candlelight because society said your brain couldn't understand numbers. That was the life of Marie-Sophie Germain, a young woman who dared to challenge the impossible. And what she achieved? It changed mathematics forever. Today, you will learn the incredible and exciting story of the woman the world tried to silence, but who left an immortal legacy. The greatest mathematicians of all time. Episode 5. Marie-Sophie Germain.
Sophie Germain made major contributions to number theory, particularly the theory of primes, acoustics, and elasticity. She was born on April 1, 1776 in Paris, France, and died on June 27, 1831, also in Paris.
Was the middle daughter of Ambroise François Germain, 1726 to 1821, a prosperous merchant, goldsmith, and jeweler who later became silk merchant, and Marie Madeleine Gregoulou, 1728 to 1823, daughter of the goldsmith Jean Gregoulou, a friend of philosophers and political economists. Ambroise François was elected deputy to the National Assembly in 1789 and later became a director of the Bank of France. Sophie's older sister was Marie Madeleine Germain, born May 29, 1770, and her younger sister was Angélique Ambrose Germain, born 1779. Marie Madeleine Germain married notary Charles Lerbet, 1752 to 1836, in 1790, and they had a son, Armand Jacques Lerbet, 1791 to 1864, who became a lawyer, sportsman, and politician. Angélique Ambrose Germain married the physician René-Claude Geoffroy, 1767 to 1831, and after the latter's death in 1831, married another physician, Joachim Henry Dutauchet, 1776 to 1847, an important botanist and physiologist in 1833. We have provided some details about Sophie's sisters because she did not get married, and as a consequence, her sisters and their families played an important role in her life.
Sophie's house at 336 Rue Saint-Denis, where she was born, was a meeting place for those interested in liberal reforms, and she was exposed to political and philosophical discussions during her early years. The year 1789 saw the outbreak of the French Revolution, when, in May of that year, France became a constitutional monarchy, followed by the storming of the Bastille on July 14. Sophie's father was elected deputy of the Third Estate for the city of Paris, then by the National Assembly, and was very involved in political events. Sophie was 13 years old at the time, and until then she had been homeschooled. With Paris in chaos and normal life on hold, she decided that she would go to her father's library, which was extensive, and spend her time reading books. Sophie, who was 13 when the revolution broke out, leafed through her father's books and came across Étienne Montoucla's Histoire des Mathématiques. She read Montoucla's account of Archimedes' passion for mathematics. Archimedes forgot to eat and drink. His servant had to remember mealtimes for him and almost forced him to satisfy those human needs. Sophie read about Archimedes' death at the hands of a Roman soldier because he wouldn't stop studying mathematics. She was moved by the story and decided that she should also become a mathematician. Here was something that would allow her to become so involved that she would escape the chaos of the revolution that was happening around her. She told her parents that she wanted to become a mathematician, but they were totally opposed to her ideas, saying that it was not an occupation for girls.
Sophie, however, continued her studies in her father's library, beginning by reading the first volume of Étienne Bezut's Cours complet des mathématiques à l'usage de la marine et de l'artillerie, which covered arithmetic. She found a book by Jacques-Antoine Joseph Cousin, 1739 to 1800, on calculus, namely Leçons de calcul différentiel et de calcul intégral, 1777, which she found fascinating. To start reading more advanced texts on calculus, she taught herself Latin and Greek. She read Newton and Euler at night, wrapped in blankets while her parents slept. They had taken away her fire, her light, and her clothes in an attempt to wean her away from books. Eventually, her parents eased their opposition to her studies after waking up one morning, seeing that Sophie was not in her bed, and finding her asleep in the library, which was so cold that the ink had frozen in the inkwell. Although Germain did not marry or obtain a professional position, her father continued to support her financially throughout her life. Sophie continued to study differential and integral calculus over the next few years, with the horrific events around her during the Reign of Terror in 1793–94 only helping her to focus on her studies. The L'École Centrale des Travaux Publics was founded in 1794 by Lazare Carnot and Gaspard Monge. The following year, it was renamed École Polytechnique. Sophie Germain was 18 years old when the école opened and was at the ideal age to begin university studies. However, there was no way for a girl to become a student. This did not prevent Germain from obtaining handouts for several courses at the École Polytechnique, including the chemistry course by Antoine-François Fourcroy and the analysis course by Joseph-Louis Lagrange. At the end of Lagrange's course, he invited his students to submit their observations in writing. Using the pseudonym M. Leblanc, Germain presented an article whose originality and insight led Lagrange to seek out its author. We note that the pseudonym M. Leblanc was not a made-up name, but rather the name of the student Antoine-Auguste Leblanc, who attended the École Polytechnique. He was not very talented in mathematics and quickly abandoned his studies at the École Polytechnique. When Lagrange discovered that M. Leblanc, who had submitted a paper to him, was a woman, his respect for her work remained, and he became her sponsor and mathematical advisor. Her education, however, was disorganized and haphazard, and she never received the professional training she wanted. Lagrange certainly warned his colleagues that Germain was a girl with mathematical talent, and several of them wrote to him. Monge, for example, wrote to her about problems associated with a lever when infinitesimal changes occur in the position of a weight. Others discussed certain mathematical paradoxes with her. There was, however, no attempt to provide structured learning, although Jacques-Antoine Joseph Cousin offered to meet her. It is worth noting that since Germain was an unmarried woman, there were social difficulties in her encounter with men.
Not everyone treated her with the respect she felt she deserved. One case was that of Jérôme Lalande, who visited Germain in 1797. She began talking to him about Laplace's World System Exposition, which had been published only the previous year. Lalande told her that she should not read such works, but rather the second edition of her book Astronomie des Dames, 1795. This Astronomy for Checkers does not contain a single mathematical equation, and Germain was insulted by his suggestion. Lalande sent her a letter of apology on November 4, 1797, but she never forgave him. Another who offended her was the Hellenist Anos de Villasson. He did this by praising her in a poem he had written, and we know how displeased she was by Villasson's letter of apology written to her on July 14, 1802. Mademoiselle, I dare to take the liberty of offering you, as an enclosed, a sample of the new edition of my unfortunate work, with the corrections and additions I have mentioned. Monsieur Poggens, mademoiselle, inserted it in the third number of his Bibliothèque Française, before I suspected that the homage to truth would shock her modesty, as rare as her talent. I repeat with my apologies and living an eternal repentance, on my word of honor,
that I would never have been permitted to speak of you, mademoiselle, in writing, and that my admiration will always be silent and chained by the desire to obtain forgiveness for a mistake or for an involuntary fault, and for the deep respect I swore to your mother and sister. I am honored to be, mademoiselle, your humble and obedient servant, Anos de Villasson.
Germain wrote to Legendre about problems suggested by her Essai sur la théorie des nombres of 1798, and the subsequent correspondence between the two became practically a collaboration. Legendre included some of his findings in a supplement to the second edition of Théorie. Several of his letters were later published in his Oeuvre philosophique de Sophie Germain. However, Germain's most famous correspondence was with Gauss. She had developed a thorough understanding of the methods presented in her Disquisitiones Arithmeticae of 1801. Between 1804 and 1809, she wrote him a dozen letters, initially adopting the pseudonym M. Leblanc again, for fear of being ignored because she was a woman. After receiving his first letter, Gauss wrote to the astronomer Heinrich Wilhelm Matthias Olbers, 1758 to 1840. I have recently had the pleasure of receiving a letter from Leblanc, a young mathematician from Paris, who has enthusiastically become acquainted with higher mathematics and has shown how deeply he has penetrated into my Disquisitiones Arithmeticae. During the correspondence, Gauss highly praised the proofs of number theory, an assessment he repeated in letters to his colleagues. Germain's true identity was only revealed to Gauss after the French occupation of his hometown of Brunswick in 1806. Recalling Archimedes' fate and fearing for Gauss's safety, she contacted a French general who was a friend of her family. Gauss knew neither the general nor Sophie Germain, and after he asked questions, she was forced to reveal her identity, writing to him, "I am not as completely unknown to you as you may believe, but fearing the ridicule attributed to a female scientist, I have previously adopted the name M. Leblanc when communicating with you. I hope that the information I have entrusted you today will not deprive me of the honor you have bestowed upon me under a borrowed name." When Gauss received this letter, he praised it even more. He writes, "But how can I describe to you my admiration and astonishment at seeing my esteemed correspondent M. Leblanc metamorphose into this illustrious personage, Sophie Germain, who gives such a brilliant example of what I would have difficulty in believing. The taste for abstract sciences in general, and especially for the mysteries of numbers, is exceedingly rare. We are astonished at this. The enchanting charms of this sublime science reveal themselves only to those who have the courage to delve into it. Indeed, nothing could prove to me so flattering and less equivocal that the attractions of this science, which has enriched my life with so many joys, are not chimerical, like the predilection with which you have honored it."
We have already mentioned that Sophie's younger sister, Angélique Ambroise Germain, married the physician René Claude Geoffroy in 1809. He had a beautiful house at 4 Rue de Broc in Paris, and sometime after the wedding, the whole Germain family moved into that house. Let us also note that Sophie became close to her nephew, Armand Jacques Lorbet, the son of her older sister. She appointed Lorbet as her literary executor, and indeed, after her death, he would publish some of her unfinished works. In 1808, the German physicist Ernst Florenz Friedrich Chladni, 1756 to 1827, visited Paris, where he conducted experiments on vibrating plates displaying the so-called Chladni figures. The Institut de France has launched a prize competition with the following challenge: formulate a mathematical theory of elastic surfaces and indicate how it agrees with empirical evidence. A 2-year deadline was established for all registrations. Most mathematicians did not attempt to solve the problem because Lagrange had said that the available mathematical methods were inadequate to solve it. Germain, however, spent the next decade trying to derive a theory of elasticity, competing and collaborating with some of the most eminent mathematicians and physicists. In fact, Germain was the only participant in the contest in 1811, but her work did not win the prize. She had not derived her hypothesis from principles of physics, nor could she have done so at the time because she had no training in analysis and calculus of variations. His work, however, sparked new insights. Lagrange, who was one of the judges of the contest, corrected the errors in Germain's calculations and came up with an equation that he believed could describe Chladni's patterns. The contest deadline was extended by 2 years, and again Germain submitted the only entry. She demonstrated that the Lagrange equation produced Chladni patterns in several cases, but failed to provide a satisfactory derivation of the Lagrange equation from physical principles.
For this work, she received an honorable mention. Germain's third attempt at the reopened contest of 1815 was deemed worthy of the prize of a 1-kilogram gold medal, although deficiencies in his mathematical rigor remained. To the public's disappointment, she did not appear as expected at the award ceremony. Although this was the high point of her scientific career, it has been suggested that she felt that the jurors did not fully appreciate her work and that the scientific community did not show the respect that seemed due to her. Certainly Poisson, his main rival on the subject of elasticity and also a judge of the contest, sent a laconic and formal acknowledgement to his work, avoided any serious discussion with it, and ignored it in public. Although it was Germain who first tried to solve a difficult problem, when others with more training, skill, and contact drew on his work and elasticity became an important scientific topic, it was excluded. Women simply weren't taken seriously. Germain attempted to extend his research in a paper submitted in 1825 to a commission of the Institut de France, whose members included Poisson, Gaspard de Prony, and Laplace. The work suffered from a number of shortcomings, but instead of reporting them to the author, the committee simply ignored the paper. It was recovered from Prony's papers and published in 1880. Among her work done during this period is work on Fermat's last theorem and a theorem that became known as Germain's theorem. This would remain the most important result related to Fermat's last theorem of 1738 until Kummer's contributions in 1840. She wrote to Gauss on May 12, 1819. Although I have worked for some time on the theory of vibrating surfaces, to which I have much to add if I had the satisfaction of doing some experiments on the cylindrical surfaces I have in mind, I have never stopped thinking about number theory. Long before our Academy proposed as the subject of a prize the proof of the impossibility of Fermat's equation, this challenge, it has often tormented me.
Larry Riddle writes, "In this letter, she made a significant contribution by proving case I of the theorem to a set of prime exponents, the so-called Sophie Germain primes. Germain's theorem established that if a prime number p has an auxiliary prime factor p of the form 2p plus 1, where p is prime, then there are no primitive solutions, not divisible by p, to Fermat's equation." His letter and manuscript, found in various libraries, showed his analysis of the cousins p less than 100, and for auxiliary primes with n from 1 to 10. However, as Germain admitted to Gauss, she failed to establish the existence of an infinite number of auxiliary primes, even for a single prime exponent. In fact, Germain's grand plan was doomed to failure, as it was later shown that for every odd prime p, there are only a finite number of auxiliary primes that satisfy the non-consecutives. Germain herself ended up proving in a letter to Adrienne Marie Legendre that for p equals 3, auxiliary cousins 7 and 13 were the only ones that worked. However, this was the first time anyone had devised a plan to prove Fermat's last theorem for infinite prime exponents, rather than analyzing it on a case-by-case basis. In 1985, using a generalization of his method, Adelman and Heath-Brown and independently Fouverie-Brun-Titchmarsh theorem
proved that the first case of Fermat's last theorem is valid for infinite exponents.
Germain continued to work in mathematics and philosophy until his death. Before her death, she was drafting a philosophical essay that was published posthumously as Considérations générales sur l'état des sciences et des lettres. His article was highly praised by Auguste Comte. Ami Dahan del Medico writes, in the essay, she tried to identify the intellectual process in all human activities. She believed that the intellectual universe is full of analogies. The human spirit recognizes these analogies, which leads to the discovery of natural phenomena and the laws of the universe. We must recognize the analogies between Sophie Germain's life and our own, and they must lead us to strive for excellence in the face of prejudice. Jesse A. Fernandez-Martinez notes how Germain anticipated Auguste Comte. Comte's debt to Condorcet and Saint-Simon has often been mentioned. It has only recently been discovered how distinctly it was anticipated by Sophie Germain in the main features of her system. During, in his Critical History of Philosophy from its beginnings to the present time, states, after presenting a complete summary of his work, it is seen from the foregoing that the positivism, which, without the use of the word, is found in the writings of Sophie Germain, contains the essential characteristics of what has hitherto been associated with the name of Auguste Comte. She was stricken with breast cancer in 1829, but, undeterred by this and by the struggle of the Revolution of 1830, she completed papers on number theory and on the curvature of surfaces, 1831.
Germain died in June 1831 at 13 Rue de Savoie in Paris, which still stands today and has a commemorative plaque. Her death certificate listed her not as a mathematician or a scientist, but as a rentista, real estate owner. In 1913, the National Journal of Mathematics, number 14, cites H.J. Monin's Woman in Science, 1913. And yet, strange as it may seem, when the civil servant came to draw up the death certificate of this eminent associate and collaborator of the most illustrious members of the French Academy of Sciences, he designated her as rentière annuitante, not as mathematicienne. And that's not all. When the Eiffel Tower was erected, on which the engineers were obliged to pay special attention to the elasticity of the materials used, the names of 72 sages were inscribed on this lofty structure. But the name of that daughter of genius, whose research has contributed so much to the establishment of the theory of the elasticity of metals, Sophie Germain, will not be found in this list. Was she excluded from this list for the same reason that Ignacy was ineligible at the French Academy, because she was a woman? It seems so. If such indeed was the case, the greater the shame for those who were responsible for such ingratitude to one who deserves so much from science and who by his achievements earned an enviable place in the Hall of Fame. Germain was buried in the Père Lachaise Cemetery. Marie-Sophie Germain proved that the true genius knows no barriers of gender, prejudice, or time. Her courage not only transformed mathematics, but also opened doors for all the women who came after her. If this story inspired you, imagine how many others are still hidden, waiting to be told. So sign up now, activate the bell, and join us in revealing the secrets and amazing lives that history has almost erased. Because the next reveal could be even more surprising than you think.